Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries. We are on day 30 of our hashtag 30 Days of Code Challenge with Educative. Today's problem is the final one of this challenge, and the problem is frog position after t seconds. Let's get into it.
And for the final challenge, we're diving into a deceptively complex problem that mixes probability, graph theory, and tree dynamics all at once. Frog position after t seconds, LeetCode 1377. By the end of this breakdown, you'll understand the entire system as a clean, predictable flow of probability down a tree. Let's dive in. The setup is simple. A frog starts at node 1 of a tree. Each second, it does one of two things. First, if the node has unvisited neighbors, the frog must jump to one of them, uniformly at random. Second, if there are no unvisited neighbors, the frog stays where it is. After exactly t seconds, what is the probability that the frog is sitting on the target node? This problem sounds like a random walk, but the trick is that it's not random chaos. Because this is a tree, the structure gives us perfect order. Before writing any code, you need to lock in 5 rules. Rule 1, frog moves once per second. Rule 2, no revisits are allowed. Rule 3, if the frog can't move, it stays put. Rule 4, reaching the target early doesn't mean you can freeze. If the target has unvisited children, the frog must keep moving. Rule 5, if movement is possible, probability splits evenly across all children. These rules define how probability flows. At first glance, this problem looks like you have to simulate probabilities down every possible path. But it's simpler than that, because this is a tree. There are no cycles, exactly one path between any two nodes, and all probability flows downward from parent to children. So instead of chaotic random walks, we use DFS to trace every possible branch of probability. Let's look at a tiny example. We have a tree where node 1 is the root with children 2 and 3. At t equals 1, the frog must leave node 1. It randomly picks 2 or 3, so each has probability 0.5. At t equals 2, nodes 2 and 3 have no unvisited neighbors. The frog stays there. So if the target is 2 at t equals 1, the probability is 0.5. At t equals 2 or 3 or 100, it's still 0.5. This tiny example contains the core idea of the entire problem. The problem input uses edge lists like 1 to 2, 1 to 3, but we need a bidirectional adjacency list. Node 1 maps to 2 to 3, node 2 maps to 1, node 3 maps to 1. This lets us traverse children while excluding the parent, since revisiting isn't allowed. So how do you compute the probability? We do a DFS with 4 pieces of state: the current node, the parent to avoid revisits, the time so far, and the probability of reaching this node. At each DFS step, first, if we've reached time t, we freeze the probability. Second, we look at all children that aren't the parent. Third, if no children exist, the frog is stuck forever. Fourth, otherwise we split the probability evenly among all children. This gives us a clean recursive simulation. There are 3 stopping conditions that you must get correct. Case A, time equals t. We stop immediately. If the current node is the target, return its probability. Otherwise, return 0. Case B, no unvisited children, meaning we're at a leaf node. If this is the target, the frog stays, so return probability. Otherwise, return 0. Case C, reach the target early, but it has children. The frog must keep moving, so the probability of staying at the target is 0. These 3 rules solve most edge cases. Here's the DFS structure, written cleanly. We define DFS with node, parent, time, and probability as parameters. If time equals t, return probability if node equals target, else 0. Get children by filtering out the parent from the graph neighbors. If there are no children, return probability if node equals target, else 0. If node equals target but there are children, return 0 because the frog must move. Otherwise, calculate share as probability divided by the length of children. Initialize total to 0. Then, for each child, add the result of DFS with child, current node as parent, time plus 1, and share as the probability. Return total. Here is the full clean implementation of frog position after t seconds. We build the adjacency list by creating a dictionary for nodes 1 to n. Then, for each edge, we add bidirectional connections. We define the DFS function with node, parent, time, and probability as parameters. If time equals t, return probability if node equals target, else 0.0. Get children by filtering graph of node to exclude the parent. If there are no children, return probability if node equals target, else return 0.0. If node equals target, return 0.0 because the frog must keep moving. Calculate share as probability divided by the length of children. Initialize total to 0.0. Then for each child, add the result of recursively calling DFS. Return total. Finally, we call DFS starting from node 1 with parent as -1, time 0, and probability 1.0. This uses pure DFS, O of n time and O of n space. Because this is a tree, DFS only visits each node once, so the time complexity is O of n. The space complexity is O of n for the adjacency list plus recursion stack. This is optimal. You can't go faster on a tree with n nodes. DFS is perfect here because probability behaves exactly like a depth-limited search. Time t gives you a max depth. No cycles means no branching confusion, and probability splits only when children exist. If the frog gets stuck, probability stops moving. Even though this feels like a random walk, DFS makes it deterministic and structured. If you remember nothing else, remember these 3 principles. First, probability only flows downward. Second, the frog must move if possible. Third, probability freezes at time t or at leaf nodes. That's the entire algorithm.
And that's a wrap of day 30 of our hashtag 30 Days of Code Challenge with Educative. I am so proud of us for sticking through this every single day, putting in the work, coding, learning about all of these different types of problems, data structures, and algorithms. So I hope that you learned so much from this journey. And if you did, like down below, share this video with a friend, subscribe to our YouTube channel. We're going to be bringing much more different ways that you can upskill in your agentic AI learning journey. We hope to see you next time. Bye!